Welcome to MSB lecture series on the chemistry of main group elements. In my previous lecture, I was discussing about the oxy acids of group 15 elements with focus on nitrogen oxy acids, and let me continue from where I had stopped. Before I proceed on to oxy acids, let me talk about another important reagent, that is sodium nitrate. This is used in the preparation of diazonium compounds. So, that means sodium nitrate is an important reagent in the preparation of diazonium salts, which finds lot of application in organic synthesis. And in this process what happens, HNO2 is prepared in situ. So, let me write down that equation. For example, aniline, when it is treated with sodium nitrite with HCl at less than 273 Kelvin, it forms minus. So, this is where the utility of sodium nitrite comes into the picture. So, alkali metal, the nitrites when heated alone, for example, sodium nitrate with lead, when it is heated, it forms sodium nitrite through the formation of lead oxide. The product of the reduction of HNO2 nitrous acid depends on the reducing agent. For example, NO is formed with iodide or iron 2 plus, N2O is produced with tin 2 plus, and NH2OH results from reduction by SO2, and ammonia is formed when zinc used in alkaline solution. Okay. Now, let us come back to nitric acid HNO3, and of course, it is an important industrial chemical that is manufactured on a large scale in the Haber-Bosch process. Of course, Haber's process is associated with the manufacturing of ammonia starting from N2 and H2. So, let me give the sequence of reactions that are involved in the preparation of nitric acid HNO3. So, NO is first oxidized to NO2. Okay. And of course, the NO2 is in equilibrium with its dimer N2O4. So, N2O4 on treatment with water gives HNO3 and HNO2. Okay. So, this HNO2 is used in the preparation of NO2. So, treatment of NO2 with water gives nitric acid, and just recall that I had mentioned NO2 as an anhydrous of nitric acid. Okay. So, I had mentioned that NO2 is an anhydride of nitric acid. So, pure nitric acid can also be made in the laboratory by adding H2SO4 to potassium nitrate and distilling the product under vacuum. So, here H2SO4, when it is treated with potassium nitrate, it forms so thus nitric acid obtained can be distilled under vacuum to get pure nitric acid. So, nitric acid is a colorless liquid, must be stored below 273 Kelvin to prevent slight decomposition, which gives the acid a yellow color. Of course, yellow color is due to the formation of NO2. On storing above 273 Kelvin, HNO3 gives out NO2 that imparts yellow color to the acid. Nitric acid is quite reactive. For example, tin, arsenic and a few D block metals are converted to their oxides when treated with nitric acid, but others form nitrates. Let me show you some important reactions of nitric acid with various metals. Only magnesium, manganese and zinc liberate H2 when they are treated with dilute nitric acid. In case of copper, we get both NO as well as NO2 depending upon the nature of the nitric acid. For example, when copper is treated with dilute nitric acid, that leads to the formation of NO, whereas the treatment of copper with concentrated nitric acid leads to the formation of NO2. Let me write these two equations. Okay, so you should remember here copper on treatment with dilute nitric acid gives NO, whereas copper when it is treated with concentrated nitric acid it gives NO2. Of course, in both the cases formation of copper nitrate is observed, only difference is between the formation of NO and NO2. Aqua regia contains free chlorine and ONCl and attacks gold and platinum with the formation of respective chlorocomplexes. So, to make any coordination compounds or organometallic compounds, gold metal is first dissolved in aqua regia to form this aric acid HAUCl4 and then further reagents are added to make the specific compounds containing gold. Now, let us look into the oxides of phosphorus. Oxides of phosphorus include P4O6, that is phosphorus trioxide, and P4O10 phosphorus pentoxide, both of which are cage compounds having tetrahedral geometry. Phosphorus trioxide P4O6 is obtained by burning white phosphorus in a restricted supply of oxygen. It is a colorless volatile solid having melting point 297 and boiling point 447 Kelvin. Each phosphorus atom in P4O6 carries a lone pair of electrons, and thus P4 can be considered as a Lewis base. Adducts with 1 or 2 equivalents of BH3 have been reported. So, in case of phosphorus trioxide, the PO bond distance, let me write the structure for you. So, this is phosphorus trioxide. Okay, so, here these lone pairs are still intact. As a result, this can perform as Lewis base, and the PO distance is 165 picometer, and POP bond angles are anywhere between 128 to 99. This oxide is soluble in diethyl ether or benzene, but reacts with cold water. So, that means this is P4O6. When it reacts with water, it forms H3PO3. Okay. The solid state structure confirms that dimerization from P2O3 to P4O6 occurs through PO bond cleavage, okay, in structure and reformation of PO bonds between the monomeric units. And of course, free P8O12 has not to date been isolated. One can also prepare P2O6 by reacting P4 with restricted amount of oxygen. Reaction of P4O6 with one equivalent of dimethyl sulfide adduct of BH3 followed by slow crystallization from toluene solution leads to an adduct of the dimer of P4O6, that is P8O12. Let me write the structure for you. You can see here we have 1, 2, 3, 4, 5. So, this is one of the PO bond is broken, and now we have another such unit comes here. Okay. So, now this phosphorus lone pair is donated to BH3. Okay. So, this is P8O12 BH3 twice. Okay. So, this was crystallized in toluene solution at 244 K. Okay. And of course, this was made by treating P4O6 with BH3 adduct of dimethyl sulfide. You may be having some doubt that why only two of them are coordinated. Of course, although this has 4 phosphorus with each one lone pair, these compounds are highly hygroscopic and highly reactive. As a result, reaction of this one and isolation is very difficult, and that is for the same reason, because of its high reactivity, the free form of P8O12 P8O12 in its pure form is not isolated. However, this compound has been crystallized and the structure has been determined using single crystal X-ray analysis. Nevertheless, these type of compounds are highly reactive, and using them as Lewis bases to interact with transition metals is very difficult task. But the most important oxide of phosphorus is P4O10, that is phosphorus pentoxide. It can be made directly from P4 and using excess of oxygen, or we can also call oxidation of P4O6 also gives P4O10. P4 plus 5O2 gives P4O10. Okay. And in the vapor phase, phosphorus pentoxide contains P4O10 molecules with structure having this kind of again this is very similar to P4O6, except for the fact that phosphorus do not have lone pair and each phosphorus has a terminal double bonded oxygen. So, this one is P4O10. Of course, P4O10 is highly hygroscopic. It can readily undergo hydrolysis to form phosphoric acid. Okay. There are 3 other oxides of phosphorus. They are essentially P4O7, P4O8 and P4O9. Of course, these 3 structures are related to P4O10 as well as P4O6. For example, if we take P4O6 and start oxidizing one phosphorus at a time, we can start getting this one. For example, in case of P4O7, one of the phosphorus atom is oxidized from P4O6, and if you oxidize 2 of them, it will P4O8, and if you oxidize 3, leaving the lone pair on one phosphorus intact, that is P4O10. That means writing the structures is not at all difficult. You can see those structures I have shown here. This is P4O6 and this is P4O10, and of course, here the adduct of dimeric P4O6, that is P8O12, and here you can see P4O6 when it is oxidized, one of the phosphorus atom is oxidized to P5, it gives P4O7. Similarly, 2 of them on oxidation gives P4O8, and all the 3 are oxidized, leaving only one in trivalent state, it becomes P4O9. So, in contrast to the high stability of phosphorus 5 oxide, arsenic, antimony and bismuth more readily form oxides with oxidation number +3, specifically As2O3, Sb2O3 and Bi2O3. In the gas phase, arsenic and antimony oxides have the molecular formula E4O6, okay, and of course, E is arsenic or antimony. Condensation of As4O6 vapor above 520 Kelvin leads to the formation of As2O3 glass. That means, if you take As4O6, okay, above 520 Kelvin, okay, it leads to the formation of As2O3 glass. Okay. So, dissolution of As2O3 in water gives a very weakly acidic solution, and it is probably that the species present as ASOH thrice. Although this has never been isolated, crystallization of aqueous solution yields As2O3. So, if you take the aqueous solution of As2O3, that yields As2O3 crystals. Okay. So, arsenic trioxide dissolves in aqueous alkali to give salts containing ASO2 minus ion. So, arsenic trioxide, that is As2O3, okay, dissolves in alkali to give ASO2 ions, okay. Whereas in aqueous HCl, it gives AsCl3. The properties of Sb2O3 in water and aqueous alkali or HCl is very similar to arsenic oxide. That means, antimony behaves in a similar fashion. Bismuth 3 oxides occur naturally as bismite and is formed when bismuth combines with oxygen on heating. And As2O5 has a lattice structure consisting of ASOSI linked octahedral ASO6 and tetrahedral ASO4 units. So, if you take As2O3 and treat this one with concentrated nitric acid, it forms H3ASO4 similar to phosphoric acid, and this one on dehydration gives an oxide analogous of P2O5, that is phosphorus pentoxide. This is arsenic pentoxide. So, arsenic pentoxide has ASOS linked octahedral ASO6 and tetrahedral ASO4 units. Now, let us look into the oxo acids of phosphorus, and this is an important group of compounds, but the acids are difficult to classify in a very straightforward manner. It should be remembered that basicity of each acid corresponds to the number of OH groups, not simply to the total number of hydrogen atoms, but how many OH groups are there will decide whether it is a dibasic, monobasic or tribasic. Diagnostic absorptions in the IR spectrum of H3PO3 as well as that of H3PO to confirm the presence of pH bond. Of course, one can also look into the phosphorus NMR to see whether pH bond exists. In that case, we will see a characteristic 1J pH coupling, and phosphorus attached to hydrogens do not ionize in aqueous solution. One should remember, when phosphorus is attached to hydrogen, they do not ionize in aqueous solution. Let me talk about phosphinic acid before I conclude this lecture. Phosphinic acid is H3PO2. Okay. So, the reaction of white phosphorus with aqueous alkali produces phosphonate ion, that is H2PO2 minus. Okay. By using barium hydroxide as alkali, precipitating Ba2 plus ions as BaSO4 and evaporating the aqueous solution with deliquescent crystals of H3PO2 can be obtained. So, that means by using barium hydroxide as an alkali and precipitating Ba2 plus ions as BaSO4 and evaporating the aqueous solution, white deliquescent crystals of H3PO2 can be obtained. In aqueous solution, phosphinic acid is fairly strong monobasic acid. Okay. So, phosphinic acid and its salts are reducing agents. NaH2PO2 is used industrially in a non-electrochemical reductive process. So, this finds application in non-electrochemical reductive process. Okay. So, when phosphinic acid is heated, it undergoes disproportionation and gives pH3 and H3PO3. For example, on heating, phosphinic acid forms pH3 and H3PO3, or one can also write this equation in a different way. So, that means essentially one can get either H3PO3 or H3PO4 along with pH3 when phosphinic acid is heated. Now, let us look into phosphonic acid. This is H3PO3. Okay. Of course, one can prepare phosphonic acid by treating P4O6 with water, or on subjected to hydrolysis, P2O6 gives H3PO3 phosphonic acid, and pure phosphonic acid is colorless quiescent crystals having melting point 343 Kelvin. In the solid state, the molecules of the acid are linked by hydrogen bonds to form a 3-dimensional network. Okay. So, let me discuss some more aspects of phosphorus acids in my next lecture. Until then, have a pleasant reading of group 15 chemistry. Thank you very much.